Welcome everybody to Thermodynamics. I'm John Sullivan and the professor for the course. What I would like to draw your attention to right now is, the syllabus that we have for, our summer session. So I have my contact information here. I do use email very extensively, so please use my email address whenever possible. We've also set up a MyWPI site, and there is a discussion board within there. Using that discussion board will help, because if you have a question, I'm sure other students have a question as well. Note that I'm not requiring a textbook. However, the Moran textbook, The Fundamentals of Engineering, is a superb textbook. If you are going to deal with anything in thermodynamics, you would do very well by picking this book up. I do not need to see the 7th edition. The homeworks that I post, and I will post them today, I will provide the course or the problem number from the book, but I will also provide the actual problem statement as well. So you don't need to have this particular book in order to do the course. However, if you do use a different book, it'll be your responsibility to figure out which sections you need to read within your textbook. So our course description. Thermodynamics is going to emphasize, system and control volume modeling. We're going to do the first and the second law of thermodynamics. The first law of thermodynamics is the conservation of energy. You should have a background of your basic physics, and we will not do a lot of calculus, but a lot of times we have to integrate 1 over the volume in order to come up with a log type system. Note that, depending upon what the course composition is for who is there and stuff, we might change some of the syllabus. I do note that at least one of you is from BME, and maybe we should have a few more BME related type problems. The homeworks are going to be assigned, pretty much on a weekly basis, and they will be due the following week. So you have approximately a week to do the homework problems. They should not take you an entire week to do. So if you have other obligations that are going to take up several days during that week, it still should not be a problem to complete the homeworks. I'm going to give 4 exams. I don't have a specific date on the exam because this is an online course, and I have to see how it does flow, how the interaction between you and I exists before I can continue to explicitly state the date. But given that there are 4 exams and there are 7 weeks to the course, approximately every week and a half we will have an exam. The participation, I really do want participation from you. I want you to figure out how you can best communicate with me and with the other students in the class. Initially, I would like to use the discussion board. I am trying to get the IT department set up so that we can offer an edX style, course. And if that does happen, I will certainly let you know. Once again, the homework is going to be 15%. I will drop the lowest homework. The exams is 75%. I will drop the lowest exam. And your participation will be 10%. For student disabilities, if you have a disability, it would be important that I know this. Please contact me. The work that you do, I am expecting it to be your work. If you post a question on the discussion board to say, I'm having a hard time figuring out what the flow work is of this problem, and another student replies within the discussion board, for that, I integrated my P dV type expression. And that allowed me to calculate the flow work, or I took what the area under the integration was from our pressure versus a volume type diagram. Those type of directions and help are good. What I don't want to see on the discussion board is that, oh, I integrated our PDV and I got the log of V2 minus a log of V1 divided by 2 to give an answer of 15. I don't want you to provide the answer. I want you to provide help. And that will go a long way toward participation, but it will also keep the academic honesty intact. So, for our schedule, this week, week 1, which we are in now, we will cover all of chapters 1 and 2. In the second week, we will cover chapters 3, and etc. So this schedule should be in pretty reasonable form. Toward the end of the system, I really do want to get into power systems and actual real engineering applications for the thermodynamics. The course is thermodynamics. What is thermodynamics, and why is it that we are studying it? Why is it a required course for all mechanical engineering students? So thermodynamics, it really does deal with the science of how matter behaves in relationship to heat and work. If you think about it, what happens when you take ice and you add heat to it? It changes phase into water. Or when you take water and add heat into it, it changes phase and turns into steam. That is the thermodynamics. So when we are dealing with matter as a solid, that's really not thermodynamics. That's much more your ES 2001 material science. If you are studying liquids, then we are definitely in the area of thermodynamics, as we are in the area with gases. Plasma is certainly a thermodynamic area, but it's well beyond the scope of this course. So I would leave that to your graduate school studies. Now, the applications of thermodynamics, as listed in your Table 1 of Chapter 1, the applications, they are huge. This system really shows how our solar cells related to thermodynamics. What about power plants? We use power plants all the time, and they are all thermodynamics. Similarly, a vehicle for an engine. What happens when that engine is running? How do you get the combustion, the exchange of heat for power? What happens in your lungs as you are exchanging energies? What happens as the heart is performing the work? That heart is pumping, and as it pumps, it increases pressure, it causes flow. All of that is thermodynamics. So thermodynamics really involves the design and the analysis of many, many engineering systems. And these systems are frequently described in later courses such as fluid mechanics, heat transfer, and to a lesser extent, structural analysis. Another description, shall we say, of thermodynamics is...
What are thermodynamics? Those aspects of physics dealing with the relationships and conversions between heat and other forms of energy. The word thermodynamic comes from the Greek words therm, which means heat, and dynamis, meaning power. The famous first law of thermodynamics states, no form of energy can be created or destroyed, but only transformed from one form to another. Therefore, the total energy in the universe remains the same. Thermodynamic principles are used everywhere. The engines of cars are thermodynamic cycles. Power plants transfer heat from a hot source, such as burning coal, to heat water that powers turbines using thermodynamic design. And your fridge at home uses thermodynamic devices too. Thermodynamic ideas are used in designing chemical reactions, for instance, hot or cold packs to put on a sore shoulder. And that's what thermodynamics involves.
Okay, so our course objectives are that the thermodynamics is a branch of science, and within that branch, what we do have is the study of the properties of matter. Those properties of matter are things that you're well aware of, such as temperature that you might have, or pressure, or to a lesser degree, specific volume or density, and other terms that are very much thermodynamic terms that you probably don't have a strong grasp on are the enthalpy and the entropy, but we will discuss those to a great extent. And we want to figure out the governing laws that can be used to describe the behavior of this matter with its interactions with the surroundings. So you're going to have to learn how to identify a system. A lot of times the system is actually a control volume, and you're going to use the thermodynamic analysis to describe, its behavior. You need to understand how to apply these concepts. It will allow you to state whether or not energy is being conserved and whether or not the pathway that it is taking is even physically possible. So after completing the course, you really should be able to define, describe properties, processes that thermodynamic analyses use. You should be able to apply the control volume analysis in order to figure out what type of steam and mass flow rate I need to run a turbine to generate 1,000 megawatts, and I can figure out how much energy as far as coal or oil I need in order to do that. Or you have a refrigerator and you need to figure out what is your cooling ranges that you have as well as its capacity. Similarly for heat pumps that we will be doing. These are the items that you will be doing with thermodynamics. And with that, we will move into Chapter 1.